Welcome to Pomodoro Joe for Wednesday, May 17th, 2023. Today we're doing LeetCode problem 2130, maximum twin sum of a linked list. This is a medium problem. In a linked list of size n, where n is even, the ith node, 0 indexed, of the linked list is known as the twin of the n minus 1 minus ith node. If 0 is less than or equal to 1, which is less than or equal to n divided by 2 minus 1. What? Okay, let's move on and we'll come back to this. For example, if n is 4, then node 0 has the twin of node 3, and node 1 is the twin of node 2. These are the only nodes with twins for n equals 4. The twin sum is defined as the sum of a node and its twin. Given the head of a linked list with even length, return the maximum twin sum of the linked list. Okay, so this whole thing about the ith node being the twin of the n minus 1 minus ith node, given these constraints, that's just a very precise but confusing way of saying these nodes have a twin that is the mirror image node. So if you divide our linked list into sort of two halves, then our node at index 0, or we can just say the first node will have a twin with the last node. Our second node will have the twin of the second to last node. Our third node will be a twin of the third to last node, so on and so forth. So that's all that means. Looking at these examples here, 5 and 1 are twins, 4 and 2 are twins. Those both add up to 6, so our result will be 6. Second example, 4 and 3 are twins, 2 and 2 are twins. The maximum sum is going to be 4 plus 3, and that's 7, so that's our result. And the last one, we just have 2, so we just sum them, and that's our result. Okay, and it looks like we do have some constraints. We have between 2 and 10 to the 5th nodes, so we have at least 2 nodes. That's good to know. All right, so we will put 25 minutes on the Pomodoro timer, and we will get started. Now, I will say, we're going to have to employ a couple different tricks to solve this problem. And I've got this diagram here. So, our linked list in this example 1 goes from 5 to 4 to 2 to 1. So 5 goes to 4 to 2 to 1. Now you noticed it's a singly linked list, so you can only go from the head to the tail, or in this case it's going to be from the left to the right. Now what we really want to do is be able to access our nodes. Ideally it'd be nice to grab them at any index. So we could dump this whole thing into a list or into an array, and then we can index into them. But I think that's going to be way too much memory and way too much processing. So let's try to do this in place with our linked list. So I think the algorithm we want to employ is either go from either end, so that's going to be from the head and the tail moving toward the center from each side, or starting at the center and move out to the edges. So if we start from the outside and move in, we want to start from the left and move to the right, and we also want to start from the right and move to the left. Or if we start from the center and move out, we want to start in the center or just left the center and move to the left, and just right of center and move to the right. Now you notice these arrows for our ideal algorithm, they point in opposite directions. So if we move from the outside in, one side points to the right, the other side points left. And if we move from the inside out, then one side points left and the other side points right. Either way, we want to traverse our list in opposite directions. Unfortunately, because we just have a singly linked list, we can only traverse it in one direction. So that's going to be a problem. But we can solve this problem. We can reverse our linked list, or half of it anyway. So we don't need to reverse the whole thing. We could just reverse half of our linked list, which would allow us to traverse one half in one direction and the other half in the opposite direction. So that's our plan. We will be reversing our linked list, or half of it. Now the next trick that we have to use is to find the half of our linked list. We need to find where's the halfway mark. Now we're not given the n value. So it says we have a linked list of size n, but they don't give us n. So we could traverse the entire linked list, we could keep a count, then we could traverse and keep track of our count and just go half of the count to find the middle point. Or we could use a fast and slow pointer. So I'll be using that. So the fast and slow pointer algorithm is fairly straightforward. We'll have two pointers to our list. One we will move 2 nodes at a time. The other one will move 1 node at a time. So one pointer will be the fast pointer. It will be moving 2 nodes at a time. So it moves twice as fast as our slow pointer, which only moves 1 node at a time. So if we move them both in a loop, then our fast pointer will reach the end before our slow pointer. And at the point where our fast pointer reaches the end, our slow pointer will have moved half the distance, or exactly half our list. So that's how we find the midpoint of our list. Then from there, we can reverse 1/2 of the list, and we can do our traversal summing our pairs or twins. Okay, so let's start with a result, and we'll set it equal to 0. And at the end, we will return our result. Okay, so the first step, I'm just going to go through, we'll break this down into pieces. Let's just find the midpoint. So typically you use something like fast and slow. So the fast node and the slow node. So these are just pointers to nodes in our list. Our slow node will start at the head of our list, and the fast node, well, we can actually start this at the head's next node because we already know, at least according to our constraints down here, we have at least 2 nodes in our list. So our fast pointer will start at head.next. That just gives us a little bit of a head start. Okay, so while we still have some fast.next node, so at this point, we're going through and we'll be advancing our slow pointer 1 node at a time, and we'll advance our fast pointer 2 nodes at a time. So slow, that's going to equal slow.next. And fast will equal fast.next.next. So we're doing twice as fast with our fast pointer. And just for kicks, I'm going to print out our results here just to see what we're getting. Okay, so I'll be printing out the value of the slow pointer and the fast pointer at the end here. This is just a test to show you where we're ending up. All right, so our slow pointer will point to 4 while the fast pointer gets to the end. That looks like it's the right, that's the center. What about this one? Slow pointer points to 2 and the fast pointer gets to the end. In the last case, so in the last case, we actually don't traverse at all. Okay, so this seems to be working. We're getting to the center of our list. All right. Now the next piece, we need to start reversing 1/2 of our list. Now I could traverse the entire list once, reset our fast pointer to be the center, go from the center right and flip all of those nodes. Or we could actually start reversing our list as we traverse the first time. So as we're moving our slow node, let's just reconnect all the slow node pointers to point in the opposite direction. So we'll be reversing this left half of our list as we traverse it. Then when we get to the center, our slow node will be the head of a new list that points back to the head of our input list. So it'll be from the center out to what is our current head. Okay. So let's do that. Now, this is going to be a little bit tricky. I'm going to rename some of these nodes just because slow and fast don't really make as much sense when you're trying to reconnect things. So I'm going to rename some of these here. So we're going to have, let's see, there's going to be some node 0. Okay, so if our slow node is this node at node 1, for example, when we move from node 1 to node 2, so we're moving this up to here, we want to reconnect this link here. So we'd want to, let's see here, have it point in the opposite direction. So we'll need to keep track of this node 1 so we can point back to it. We'll need to keep track of this node 2, and we will also need to keep track of the node that node 1 was pointing to because we've changed this one. So this node 1 has to be pointing back to node 0. Oh man, this is going to be a little bit tricky, but let's see how we do. All right, I'm going to change these nodes. So the slow node, I'm going to say that this is node 1. Fast node, and call that node 2. So the thing that comes before the slow node, that's going to be node 0. And initially, there's nothing before the node. Now, we need to actually keep track of the thing that comes before node 0, according to this. So we actually need like a node -1. That's also going to be none. Okay, so these are renamed. This is node 1. This is node 2. All right, so now as we're going through our list, we're going to be reconnecting this node 1's pointers. So how do we do this? All right, so before we move on to the next node, let's just hold on to this node. So our node 0, we're going to set that equal to node 1. We want to keep track of this current node before we move on. So let me get this diagram back up here. And I'm actually going to call this N1 next because it won't be N2. N2 is going to keep zooming on ahead. Okay, so these are kind of our pieces. We have our node 1 next, and then node 0. So as we move on, essentially we started here. This was our N1. Now we've moved on. Our N1 moves to the next node, that's N1 next, leaving behind this node 0. So we have to set this node 0 to be this node N1. Actually, I don't think this diagram is helping. This is our current node. I don't have access to this node anymore unless I keep track of it. So I'm going to keep track of this node. So this is actually going to be something we'll store and carry forward. This is our current node. What I need to do with this current node is reconnect this node here. But before I can change this node's connection, I have to keep track of where it was going. Otherwise, I lose this N1. So I'm going to set this N0. Let me drop this down. I'm going to set this N0 to where are we going? So set it to N1. Then I'm going to set the N1 to N1 next so that I can advance to the next node. Now I need to actually redo all my connections. I am not explaining this well at all. So these are our pieces. N0 was where the previous N1 had been. So that was our current node. Now we need to reconnect our N0s next to point back to N-1. So that's basically switching this pointer here to be this pointer here. And then we can move our N0, or sorry, our N-1 up to our N0. And then we can set our N0 to N1, but we do that at the beginning of our loop. So this should actually reverse all of these links in the first half of our linked list. I wish I had a better diagram. One of these days I'll get some drawing software and we can do this properly. Okay, so we've gone through, we've found half of our linked list, or we've found the center point of our linked list. We've also gone through and reversed all of these nodes. So these are linked back to the head. Now what? Well, so we have essentially two linked lists. We have one that goes from the center or just left of center all the way to the left or the head. And we have another one that goes from the right or just right of center all the way to the right. Our N1 represents this midpoint. So this is the midpoint. We want to reset our node 2 back to the midpoint. So N2 is going to be N1.next. We actually want to set it to just right of the midpoint. So N1 equals the midpoint, or just left the midpoint. So our N2 will become just right at midpoint. So that's our N1 next. All right, at this point, we've got the new heads of our two linked lists, our new lists. One starting at N1, pointing backwards to the head, and one it's starting at N2, which points to the right. And we can get our first result. So our result is going to be N1 val plus N2 val. And now we need to start traversing our list in the different directions. So N2 will continue on to the right, N1 will start going backwards. But I'm going to throw you a little bit of a wrench here. It's good programming practice not to modify your inputs. At this point, we've flipped this entire half of our list into the opposite direction, which means that this list itself, this list that gets passed into us, is completely different. We've messed it up. It's totally broken. We want to leave the list in the same state that we got it. So for that, we actually need to start flipping all of these nodes back to the way they were originally. So to do that, we actually kind of need to do some of these same things. So let's get our initial setup here. Okay, we have our N1, we now need an N minus 1, and that's going to actually equal our N2 at this point, because that was where we would have gone next, but now it's the head of the new list going to the right. So our N minus 1 is actually the head of the other list, the N2. Then our node 0 will be node 1, and our node 2 will be node 2 dot next. So we're basically, I need some diagramming. In this case, this was our N1. Now our N0 becomes this one here, and our N minus 1 becomes this one here, which is also our N2. So now we're advancing to the next two nodes along the way. All right, now we actually have to go through and add up all these twins. So I'll N1 and N2. Our result is just going to equal the maximum of our current result, or the sum of N1.val plus N2.val. And of course, we need to advance our N1 and N2. So N1 equals N1.next, and N2 equals N2.next. But we have to reconnect all of these nodes, so basically we can just grab this whole thing. It should be the same. Okay, so we're going to keep track of our previous, we're going to advance our next. Oh, but we don't want to move this at twice the rate. We're going regular rate. And then N0 next becomes N1, and N1, and negative 1, and negative 1 becomes N0. Okay. This took way longer than I expected. Let's give it a shot, see how we do. All right, we don't have fast anymore. I renamed this as N2. Let's try that again. And we don't pass. Okay, what are we missing here? We're saying it's 5, which is 2 and 3. Oh. I got these mixed up. All right. Okay, we pass, but oh man, this one's kind of brutal. All right, let's see how we do. All right, and we pass. We beat 23% for runtime and 13% for memory, so not too bad, not great. But let's see, let's say we were not being nice citizens and we decided not to flip all of these back. So let's just try this without flipping all of these back. So we'll still need these nexts, but other than that, we're just going to go through super quickly. Don't need this comment. Okay, so this will actually mess up the input list. So if any other functions are trying to use this list, it will be totally broken. But Since this is just a test function here, we're not going to worry about it. Let's not be nice citizens. Let's just destroy this list and make it super fast. Let's see if that makes a difference. And we break. This one was tricky. I had to actually take a step back and sort of reimagine all the nodes and their links to figure this one out. I did have a couple things wrong, so I was able to fix that and get back to it. Then we could do the N1 and N2. But I don't want to do that yet. That's the trick. So N2 is N1.next. But N1.next has to point back to N0. There we go. Okay. Oh man. Thanks for bearing with me on that. So let's give this a run and see how we do. Again, this is destroying the list, so I do not recommend this. Even though it gets a 99.1% for runtime. Holy smokes. Yeah, we crush it. We get 99% for runtime and 85% for memory. That is way faster than I was expecting. Oh man. Okay, I know this one's really hard to follow, mostly because I do it in my head and I'm a visual thinker and I can picture where all these nodes are in space and I can't draw them out because I don't have a good drawing program. So I apologize that this one's not the best example, but hopefully you can take a look at the code. Maybe you can tease it out and understand where I was going with this. All right, well, that is it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.